When we last met, we'd been discussing entropy, the degree of disorder. And prior to that, we'd spent a good part of this chapter talking about enthalpy, heat content. So what we want to expose you to now is, what is it actually that drives a chemical reaction? There are two forces, and those forces are the two that we just mentioned. Delta H stands for change in heat content. Delta S stands for change in disorder. And if the universe could pick the perfect combination of the two that would allow a reaction to go spontaneously, it would be an exothermic reaction and a reaction that made more disorder. This is the perfect combination for what we call a spontaneous reaction. Now, it's not always that way. You can predict if a reaction is spontaneous, that is, if it happens. And by the way, it's important to understand that the word spontaneous doesn't mean fast. It just means that the reaction happens under the specified conditions. But you can make a prediction that's not just a qualitative one, but a quantitative one, as long as you know the change in heat, enthalpy, the change in disorder, entropy, and what temperature in kelvins this change is happening. It's important also to notice that when we measure enthalpy, that's in kilojoules, and entropy is historically done in joules. So to make sure that you always convert from joules into kilojoules, and also the temperature has to be specified in kelvins. So here are the two driving forces. I wouldn't probably say that these are always, if you have an exothermic reaction, it's spontaneous, or always if it's more disorder, it's spontaneous. But when you have the two of them in combination, the reaction will happen as specified. But now let's look at some other possibilities. Well, good old Gibbs, Josiah Willard Gibbs, predicted, 100 years ago, that if a reaction is spontaneous, it can also be harnessed to perform useful work. Remember, it doesn't say exactly how fast a reaction will go, just if it actually will occur under the specified conditions. You can calculate this, Gibbs Free Energy, as long as you know the enthalpy, the temperature, and the change in entropy. And you can actually put a number to it. Here are the definitions of what each of those symbols use. You should be familiar with the last three. The first one, Gibbs Free Energy, is the energy that's available to do useful work. Delta H, change in enthalpy. Delta T, change in temperature measured in kelvins. And delta S, of course, the change in entropy. If you were to see this equation with what looks like a little degrees symbol in the upper right, that means that that's under standard conditions, which typically is at 25 degrees Celsius or 298 Kelvin and 1 atmosphere of pressure. But regardless, if you crunch the numbers out and you get a value that is negative, that's interpreted as saying that reaction is spontaneous. If, however, you crunch out the change in heat minus the product of temperature times entropy, and you get a positive value, then that is a non-spontaneous reaction. Think of it as a number line. The greater the negativity of the value gets, the more and more less below zero, the more highly spontaneous it is. Get out of the room. But the greater and greater the positive value of the delta G, then that's basically going to be hell will freeze over before that reaction happens. So the size of the delta G does indicate, in some sense, the willingness of a reaction to happen spontaneously. Now, in this table, you can see various combinations, two of which I can figure out non-numerically. For example, if I know that I have an exothermic reaction making more disorganized products, my delta G is always going to be negative, and no matter what the temperature is, that reaction will happen. Let's take the opposite of that. If I have an endothermic reaction, which the universe despises, and I'm making less disordered products, which the universe also despises, then my delta G is always a positive number, and that would never be spontaneous, no matter what the temperature is. It's when you get the last combo, hey, it's exothermic, but it's less disorder. Or it's endothermic, yet things are getting more messy in the reaction. Those are the conditions under which it's difficult to predict qualitatively. Hence, that's why we use the Gibbs Free Energy equation. So I'll come back to this concept later on, but it's important to notice that if you are exothermic reactions like it when you chill them down. So if you make the conditions chillier, then even though it has less entropy, a negative delta S, that reaction could become spontaneous if you made it cold enough. And just the opposite, and this is the part that's easier for my brain to understand, if it's endothermic, that's a reaction that wants heat. You can still have a reaction happen if we have an increase in entropy, but if they're both positive, one of the ways that I can make sure that that reaction would be spontaneous is to make the temperature higher. That's what an endothermic reaction wants. It wants you to give it more heat to go. So for example, let's use our common sense. Doesn't solid water turn into liquid water? Ice melts. And the driving force for that is that ice is more disordered than liquid water, but even though it's endothermic, the reaction will still happen as long as the temperature is warm enough. You got to get it warm enough to melt the ice. So let's not fool around with this anymore. If for some reason you calculate a delta G and you get a zero value, neither positive nor negative, that just means you're at equilibrium. For example, with water, its freezing rate would be equal to its melting rate, and there would be no further change in the system. But let's not deal with that one right now. Let's go to some specific sample problems. Now at this point, if you haven't gotten one yet, please get your calculator and be ready to do these calculations. If I'm going to do the famous Haber process, nitrogen and hydrogen makes ammonia, I could either calculate a delta H by doing products minus reactants, or delta S, products minus reactants of entropy, or in this particular case, we could just give you the values. But once you have those two values, once again, joules is the unit for entropy, kilojoules is the unit for enthalpy. You can't mix apples and oranges, so be sure you always change your entropy value into kilojoules by dividing by 1,000. Shortcut way, move the decimal point 1, 2, 3 places to the left. This is where the 0.197 value came from. I don't know if it specified it or not, but let's assume that this is happening at 25 degrees Celsius. The other thing you need to do is add that to 273 to get the Kelvin. So that Gibbs free energy, or the ability to do spontaneous work, is equal to the delta H, negative 91.8, minus the product of temperature in Kelvin times the entropy turned into, and that's a typo, that should be kilojoules right there. So when you crunch the numbers out, you end up with a negative 33.1 kilojoules. The units for Gibbs free energy are the same as the units for heat. And if that's a negative number, and someone asked you, is this reaction spontaneous? Your answer would have to be yes. So what I'm going to do now is end with 3 sample problems that are embedded in your Vodcast notes. I'll be looking for, at the next time that this Vodcast is due, I'll be looking for that you have solved these and entered a value over there in the column that says delta G. And once you know the delta G, you should be able to predict if this reaction is spontaneous or not under the specified conditions. So finally, one last reminder, joules are the units for entropy. Change those into kilojoules, and the temperature needs to be specified in kelvins. Until next time.